Good morning. I'm Steve Richter with the Nature Conservancy. I'm the Director of Conservation Programs, and it's with my pleasure today to introduce Ken Bradbury as our speaker. Ken is with the Wisconsin Geological and Natural History Survey. He has been there since 1982, following his doctorate work done here at the University of Wisconsin-Madison. His dissertation took him to one of the places dear to our hearts, Door County, where he had a really rewarding and pleasurable experience. And maybe someday we'll get Ken back up there to do some work studying the groundwater impacts in that region. But today, Ken is here to describe some of his most recent work that the survey has done. And I thought it would be a very interesting presentation for all of you because we're embarking with Ken's survey as well as the United States Geologic Survey on a similar research and survey in the Mukwonago River watershed. And this is a watershed where the Nature Conservancy has, for 30 or more years, protected lands and waters in one of the healthiest rivers in southeast Wisconsin. So Ken, with that, thank you for coming.
Well, thank you, Steve, and good morning, everyone. It's a pleasure to be here, and I'm a longtime Nature Conservancy member myself, and so it's really great to talk to this group, and I see some people I know out in the audience too, and we've done projects with the TNC in the past, and I'm looking forward to doing more in the future. So today I wanted to talk about some groundwater modeling work and that we are doing, our survey is doing in two different parts of Wisconsin. But first I want to tell you a little bit about our survey. So I work with the Wisconsin Geological and Natural History Survey, and who are we? Well, we are a part of the University of Wisconsin Extension, but we have a long history. We do research, inventory, and teaching on the rocks, minerals, and water of the state. Our original survey started in 1853, believe it or not. Legislatures being similar in the past to what they are now, it was abolished and resurrected several times by the legislature. But our current structure dates back to 1897, and we've had geologists mapping the minerals and water and rocks of the state through all that time, including some famous people like T.C. Chamberlain was part of our survey. What do we do now? Well, we collect field data, we do research on the rocks and water and minerals, we make maps, we advise and teach, and we prepare reports, we prepare professional publications, we make groundwater models, which I'll talk about today. We do bulletins and maps. So we're a pretty full-service group. Here's some of our staff on a field trip. We're located in 3817 Mineral Point Road right here in Madison. We have a facility out in Mount Horeb where we store our rock and core samples, and I have an educational facility out there that some of you might want to come and visit sometime. But back to our topic today. I'm called this, Where Does the Water Come From? Groundwater models and how we use them to understand groundwater surface water relationships here in Wisconsin. And so I'll talk about today groundwater models, what they are, why we use models, and some groundwater basics, and then two examples, one right here from Dane County and another one from central Wisconsin, from the Little Plover watershed, a project that we're heavily involved in right now. First of all, what is groundwater? This group, I'm sure, is quite familiar with that, but really it's any water that's filling the cracks, pores, and interstices beneath the Earth's surface. And it's the water that we're all drinking here. All Madison's water comes from groundwater. Groundwater sustains springs, lakes, streams, wetlands. Here's some of our group surveying a spring in western Wisconsin. It sustains trout streams. That's why we have great trout streams in southern Wisconsin. The groundwater is the part of the flow that's related to what we call base flow. That's why the streams are flowing all year round, flowing in the middle of a dry summer. That's why the water is nice and cold and steady, and that's what you need for trout and many other fish species, again, as you know. It's important to discuss the water cycle and the balance of the water cycle, because that's really the most important thing to understand if you're talking about impacts on resources from using water. And again, this group is very familiar with the fact that all our water comes from precipitation, rain or snow that's falling on the land. Some of that water runs off, becomes surface water, and eventually ends up in a lake or a river. Some of it, or a lot of it, evapotranspires and leaves the Earth's surface through plants and evaporation. And then about 20 or 30% of it infiltrates through the unsaturated zone, passes the water table, which would be the dashed line here, and becomes groundwater. And when it becomes groundwater, it flows through these long, curvy flow paths to discharge either to a well, to a lake, or a stream, or a wetland, or eventually some other surface water body where it enters the cycle again. And the water that gets really down here enters an aquifer, which is going to supply water to wells. So this is a cycle, and it's a closed cycle. We don't gain or lose any water in the big scheme of things. So a water budget is like a bank account. It has to balance. I'm going to talk about groundwater modeling, and models are one way we keep track of this accounting, because it becomes kind of complicated when you're thinking of all the different places water could be. In Wisconsin, we have abundant water in most places compared to other parts of the world. But we do have some issues, and the issues are often a deficit in our water budget. And the deficit is something we can see because we see decreased base flow to springs, streams, lakes, and wetlands. That's the most obvious impact of groundwater use that we see in Wisconsin. And so we use models to look at groundwater issues. And what are some of the issues in Wisconsin? Well, the biggest one right now that we hear about in the news are regulation of high-capacity wells. How should our Department of Natural Resources approve wells? How many should there be, and so forth? Those are good questions. But other issues that you all have heard about, I'm sure, are understanding confined animal feeding operations, or CAFOs, and how they may impact groundwater. Looking at deep wells in southeast Wisconsin, around Waukesha and Milwaukee, and how those relate to the Great Lakes Compact and water supply for Waukesha, and radium in the deep aquifer. Mining issues. We had the Gogebic mine last year. It's kind of mothballed at the moment, but we also have a mining going on for frac sand in west central Wisconsin. We have a lot of mining that goes on for sand and gravel, dimension stone, and road materials. So we have all these things that have some relationship to groundwater. We think about groundwater quality as respect to nitrate, pesticides, fertilizing materials, waste disposal. We have naturally occurring contaminants like arsenic, lead. These things are sometimes naturally occurring. And then we have all the spills and contamination incidents. So these things become part of public policy, part of science, and we need to understand them. We use models to help us do that. Sometimes people seem to think that we can use water without having any consequence, that it's an infinite resource, but all water use has some consequences. So here in Madison, when we use groundwater, we have some impact on lowering water levels, changing flow paths, changing that water budget, and that can in turn impact surface water and can affect water quality. Pumping wells can cause two things. First of all, drawdown or lowering of groundwater levels, or lowering of the water table. And as I mentioned with the water budget, a reduction of groundwater flow to nearby surface water features. So it's a reduction of the natural groundwater discharge. It's a deficit in the water budget. So these are things that we need to keep track of. And just a little more about how that happens. If you have a stream or a lake here on the right, groundwater system that's flowing into that from recharge at the land surface, and the natural flow would be from recharge up here to discharge into the stream. If we put a well in there, that well is going to cause a little cone of depression, or a dimple in the water table, or a little bit of lowering here in the red circle. And that's going to capture some of the water that would have gone to the stream. And so, because everything has to balance, we have some water coming out of the well that has to be made up for by water from somewhere else, which would be less flow to the stream. And if we increase that pumping even more, we can start even pulling water back from the stream. So the pumping of the well here is reducing the flow of surface water. And understanding how big that impact is something that's very important, and it requires some calculation, and that's what we use models to help us do. So what is a groundwater flow model? A groundwater flow model is a way we use computers to solve mathematical equations that describe groundwater flow. And because the world is a complex place, we now can put in complexities of geology, recharge, pumping wells, lakes, streams, and wetlands, and heterogeneities or irregularities in the surface, and in a three-dimensional and even a transient or changing with time way to solve this question, this problem using computers. And models like this are really the very powerful tool for interpreting the past and predicting the future. And models are used all the time. They're used for weather forecasting, for building your car, for building your telephone, for many, many things in our lives today. So this is not an unusual thing at all. When we build a model, there are several steps. First, we start with the real world. We start with understanding the geology and water resources of a particular place. We have to convert that into some kind of mathematical formulation. And so if you can see up here, this map has been overlaid with a grid, a numerical grid, and each of those, it's like the pixels in your camera. Each of those little squares contains some information. The different colors represent different properties, and this one has a river in it, so the river shows up. And then we put equations into that grid, and we solve these equations with a computer. And what do we get out of it? We get a map, generally, that may show us something about predicted water levels or water flow directions or something's concentrations or flow rates or paths. And then we always have to do this step called calibration, where we compare our model back to the real world and make sure it makes sense. If it doesn't make sense, then it's not a good model, and we have to alter it or change some of the parameters in the model to make it make sense before we can actually use it for some kind of predictive way. When we're making these models, of course, as geologists, we have to collect a lot of information. So we look at the properties of the rocks. We would investigate springs, for example, measure flow in springs and streams. We would do a lot of what we call geophysics, lowering different probes down wells to measure things about the rocks and water below the surface. We have a program where we do that at the survey, and we can go down almost 2,000 feet and measure properties of the rocks and water in deep wells. Those are our windows into the subsurface. Why do we use these models? Well, they're really the current standard of professional practice, very well accepted in our science field. They're based on mathematical and physical properties, and so they give objective results, objective solutions. So often in these water resource conflicts, I see people arguing about pros and cons, and there's a lot of misinformation or mistaken information sometimes, or opinions that can't be backed up. Models are factual things, and we can put in the mathematics, and the mathematics don't lie. So they give unbiased and objective solutions. They integrate impacts from multiple stresses or multiple wells. So we can solve questions involving many, many wells at once, which is an important thing to be able to do. We get a complete water balance. We understand where all the water is coming or going. And the models are also a database of information. So all the information about a groundwater system is really stored inside a model. There's a very well-known hydrogeologist, very famous one, named John Bredehoeft, who's worked for the U.S. Geological Survey for many years. And he says hydrologists are occupied in studying aquifer dynamics. The principal tool for these investigations is the groundwater model. So let me give you two examples. The first is right here in Dane County, a county-wide model where we looked at lakes, streams, springs, high-capacity wells, and a series of bedrock aquifers that we have here in Dane County. This particular work was largely supported by the CARPC, or the Capital Area Regional Planning Commission. It's cooperative with the U.S. Geological Survey, and a lot of people who I won't name right now worked on this. Why do we do a model of Dane County? Well, if you live in Dane County, you know that there are land use issues. Here we have, these are Pheasant Branch Springs out in Middleton. Here's a development encroaching on this very nice wetland here. The kind of thing we might want to look at with a model, and we might want to think about questions like this. How do high-capacity wells, which are needed for the water supply, going to affect the surface water feature? How do land use changes, like building these houses and paving over a parking lot, how are they going to affect water resources? We can investigate those things with a model. When we make a model, we have to go out to boundaries that are distant from the place of interest. So here's Dane County. Our model boundaries, as you can see, go out some distance away to follow natural hydrologic features, like in this case the Wisconsin River or the Rock River, places where we have a good sense of what the groundwater is doing. So we take boundaries farther out than our real point of interest. We need a conceptual model, which means we have an understanding of generally what the system looks like. So here's a cross-section across Dane County. So Madison would be right in here. Here would be Lake Mendota. Out here, this would be the west side, and this would be, say, Blue Mounds out here. And this would be Koshkonong and Sun Prairie out to the east. Beneath our feet, we have, keep in mind, a cartoon, so it's more complicated than this. But in general, if we went way deep, maybe 1,000 feet down, we have crystalline Precambrian rock, something like a granite or a quartzite that doesn't have much water in it. Above that, we have a very thick series of sandstones called the Mount Simon Aquifer. These are where most of our high-capacity wells get their water. Above that, we have a thin shale unit called the Eau Claire Shale, or Eau Claire Aquitard, that limits groundwater exchange between our upper bedrock aquifer and this deep sandstone. And then on top of that, we have glacial materials, and that's where our lakes are formed. So that's our basic system, and it's important to understand we have water table aquifer up here, and we have a deep confined aquifer down here that the high-capacity wells are pumping out of. So when we put our model together, it looks something like this. Here's an oblique view of Dane County, just showing some of the features we model. We can start looking inside the model, and so this is a visualization of what we actually have in the computer. But all of these red lines represent the high-capacity wells that serve Madison and surrounding communities, and all the bluish things here represent streams that we are modeling directly, and then the blue represent the lakes, which we are also modeling. We're modeling how they go up and down in response to groundwater movement. So what you're seeing here is a cutaway of part of the model. This would be the isthmus, and Lake Mendota, Lake Monona, just to show you the subsurface complexity that's in here. All of these different colors represent different geologic units. Building a model like this, we have to do a lot of careful work to understand how these things pinch out or cut into each other. For instance, here's a valley eroded down, and the lake basin eroded down into the lower aquifer. We have lake sediment in the bottom of the lake. So there's a lot of complexity that you don't see right at the surface because this is a three-dimensional thing. We have to calibrate the model, as I said, against known water levels and groundwater flows. One of the things that we did with the Dane County model is we looked a lot at springs. There are a lot of important springs in Dane County, including the Arboretum, or the Winger Springs, which are right down the trail from where we are today. And so we measured flow in a lot of these springs, and then in our model, we compare what the model tells us, which are, in this case, would be the red bars with the blue bars, which is what we observed, and ideally would get them all to match exactly. They never match exactly because it's a model and we never get it exactly right, but this is really pretty good, a pretty good match for a groundwater model. So this is discharge of the springs in cubic feet per second. So we have all those discretely modeled, and that means we can understand where the water came from for these springs and how fast it's getting there. Got ahead of myself here. When we run the model, what do we get out of it? Well, I said we get two things. We get a water level maps and we get flow directions. So this is a simulation of the water table in Dane County. And a couple of things to note is here are the lake chain, the Yahara chain. You can see out here in the driftless area, you see all these lines close together. Those lines represent the elevation of the water table above sea level. And where the lines bunch up, that means the water table is very steep, as you might expect out in the driftless area where we have a lot more rugged landscape than we do to the eastern side of Dane County, where it's a more, the glaciated area where we have a more rolling, a little more gentle landscape. Groundwater flow is going to be perpendicular to these water table lines, and water is going to be going into the lakes. This is what we would see at the water table. Now, one of the things we can do with the models, we can look deeper. We look down into that deep aquifer. What are the lines of hydraulic head look like down there? Well, you can see they're much more gentle, and that's because they're separated from that surface topography, so they have a general appearance of the surface topography. In other words, there's a high out here near Mount Horeb where the landscape is higher. There's a low in the Yahara Basin here. But in general, the lines are very smooth, and that's because they're somewhat isolated from the surface. Now, what I've shown here are what I've called pre-development heads. That is, what the groundwater system would have looked like before we started drilling wells, so maybe 150 years ago. One of the neat things we can do with the models, we can look back in time, and then we can add the wells and see how things have changed. So now I've added all the wells, the deep high-capacity wells in Dane County, as shown by the red spots. And the size of the circle represents the amount of pumping the wells do. And as you might imagine, most of the wells are located right around Madison, but there are some over in the other communities, Mount Horeb and Stoughton and so forth. And you can see that the potentiometric surface or the head contours have changed a bit here. And again, here we're looking at elevation above sea level, but there's some closed contours around some of these wells. But we can't, looking at it this way, we can't tell how big that change has been. But if we subtract those two maps, we get something like this. This is the cone of depression, or the change in the deep potentiometric surface, or the deep water pressure in the deep aquifer between pre-development and really the present day. And so these are lines of drawdown in feet, so that you can see that the biggest drawdowns around 50 or maybe 60 feet in this area, and there's really little drawdown outside of the Madison metropolitan area, except here's some in Stoughton, and you can find Sun Prairie up here, and so forth. But the biggest impact has been right under Madison, where most of the pumping happens. Now, why should we care about that? Frankly, this is not a lot of drawdown. Our aquifer down there is nearly 1,000 feet thick. So what you might ask, it's so the water level decreases by 50 feet. Is that a big deal? Well, it doesn't. We have plenty of water. Nobody's well is going dry. But what it impacts are our lakes, streams, and wetlands, because that water, again, I'm talking about the water budget now. The water budget was changed because we had to make up for that water that was taken out of the ground. About 50 million gallons a day is pumped. That's caused that drawdown, and that lets us generate a map like this of places of all the streams and how their flows have been reduced. So in this map, a stream that's blue has had really no reduction in stream flow from pre-development to the present day, where a stream that's red or black has had a lot of flow reduction. And so you can see that around the Madison metropolitan area, there have been reductions in flow, like to Starkweather Creek, which is one that's kind of the poster child for this sort of thing. But there has been some reduction in the other streams. As we move away from that cone of depression, there hasn't been very much. So this is one way we can use a model. Another thing we can use for is look at flow paths. So here are what's called particle tracking, where we look at groundwater flow paths and how it might look and how the directions the water might travel. And I've got three views of this here. First, a map view. So look up here. And this is actually an area out by Sun Prairie. This would be the village of Sun Prairie. And I've put in these little spots just represent places that we've added mathematical particles to the model. And in map view, we let them go and see how those would move. There's a stream over here, and some of the particles, which represent drops of water, if you will, end up in the stream, others go out of the picture. Here we can do it in oblique view and see how that works, and here we can do it in cross-section. So, and in cross-section, these are some of the deep wells. And it's quite interesting to see how some of the water goes very, very deep. Some of it goes down a bit and then can arc back up and discharge to a stream. So we get a very good picture with a model of how the groundwater system is really functioning. And using this technique, we can tell where water for wells will actually come from. So here's a map of some of the wells and what's called their capture zone or zone of contribution in the Monona area. So this is the Isthmus in Madison, Lake Mendota, Lake Monona, and these funny shaped circles represent the contributing areas for municipal wells. So those little dots in the middle represent one of the Madison or Monona municipal wells, and then these different colors represent how long the water takes, most of the water takes to get to that well, whether 5 years, 50 years, or 100 years. Groundwater moves pretty slowly, and some people are surprised how small these are for 100 years. So if we want to protect groundwater around these are the areas we need to protect if we're worried about groundwater quality for these particular wells. Some of these wells that are right near the lake are actually going to get some contribution from the lakes. So using a model, we can tell where groundwater comes from and how long it takes to get there. So these are some of the planning tools that we're using the model for in Dane County. So now let's turn to a different model, and we'll move up to central Wisconsin. This will be the Little Plover River model. This is a little different model because it's a smaller model. It's at the what I'm calling the sub-county scale. And rather than a lot of bedrock, which we have in Dane County, it's a single sand and gravel aquifer, which is what we have in central Wisconsin. But we do have a lot of streams, lakes, and high-capacity wells. And funding for this work came from the Wisconsin DNR with some extra money from the Wisconsin potato and vegetable growers. And again, we cooperated on this with the U.S. Geological Survey. So Little Plover is not a huge river, but it's a very nice a river. If you've ever driven up Highway 51, past Stevens Point, you've driven across it on a bridge. It's a trout stream, and there's a very nice fishery area. So it's a highly valued resource. Where is it exactly? Well, central Wisconsin. We zoom in, so it's right here next to between Plover and Whiting, and we zoom into its drainage basin. Here's the Little Plover. The yellow line is the surface water drainage basin. Now, remember that the Central Sand Plain is a plain. It's a pretty flat, low relief area, and so the surface water drainage can be kind of ill-defined. And also remember that it's a very sandy environment, so we don't have a lot of surface runoff. Most of the water is going to either soak in or evapotranspire. We don't have a lot of well-developed drainage networks here, as we would say out in the driftless area in western Wisconsin. But we have controversy there because of the number of high-capacity irrigation wells. So this map on the right is a map of all of the Central Sands. Little Plover area is right up in here, but all these dots represent high-capacity irrigation wells that are used for irrigate potatoes, corn, beans, peas. It's kind of Wisconsin's vegetable growing area. It's a very important industry. This graph shows the increase in the number of those high-capacity wells since the 1960s, when there were hardly any, to almost 2,000 wells now. So it's a big increase, and this is the question that the DNR is faced with: how many of these wells should be approved? Because there is controversy. Controversy, as you might expect. There are factions that don't like these wells, that think that they are diminishing flow in the stream, that they are diminishing flow or water levels in lakes. There are others who say no, they're not, and there's been a lot of controversy in this area, and really hard feelings, and again, misunderstanding about how is the system really working, and how big is this problem, and what should the DNR do about it, and so again, we're trying to help this situation by giving them some concrete facts to make decisions with. So the objectives of this project were really three. First of all, to produce a groundwater flow and optimization model, and optimization means looking for the best combination of uses of these resources. There will be a science-based expert system for decision support for water management. And this particular model is to be used as sort of a pilot study for a larger model of the entire central Wisconsin area. Also, a platform to demonstrate the fundamental scientific constraints inherent to the groundwater system and give a context for different scenarios moving forward. And by the fundamental constraints, I mean that again, the things I've been talking about, that there is a water budget, that water is a finite resource and we can't violate the water budget, that water doesn't come to us from Canada. Some people still seem to think that. That there are certain things that water in this central Wisconsin is not really related to the water level in Lake Michigan, for example. Demonstrate the fundamental constraints to people, and also as an educational tool so that citizens, the potato growers, the DNR can all work from the same information base when they're making decisions and talk to each other with the same information. So our groundwater model area, again, as in the Dane County model, the model area is much larger than really the focus area, which is the Little Plover River. We chose the Little Plover River because there's a long history of groundwater studies there, a lot of data, a lot of background data, and also the DNR had some concerns about the flow in the river and some regulatory levels that they needed to meet. So that was a good place to start. All the little dots are irrigation wells, so you can see that there are quite a few. This is a three-dimensional model, has three layers, and we're using a grid spacing of 100 feet, so it's a very, very detailed model, one of the most detailed we've ever made. When we look at it in an oblique view, it looks like this. We have these different colors represent different parts of the glacial geology. These are moraines. These are some wetland deposits and so forth. So, as in the Dane County model, we have all those put into the model in 3 dimensions. One of the interesting and different things about the Little Plover project is we have irrigation going on, a lot of it. And there's been a lot of controversy about how much of this irrigation water actually ends up on the plants, how much of it actually soaks back in and becomes groundwater again, and certainly some of it does. So we really wanted, with this particular project, to look at the relationships between recharge, evapotranspiration, and irrigation, because irrigation increases evapotranspiration by putting more water onto the crops. So we can't ignore this. So we had to think about crop type, planting and harvest dates, soil properties. We actually used another kind of a model called a soil water balance model to calculate the recharge going into the system. And this is important for us to use because it's similar to what the vegetable and potato growers use for figuring out how much water they need. We wanted to use a technique that's very similar to what they're already doing so we can get some buy-in and acceptance of our work. And we've, I think, done that pretty successfully. So in this case, we're actually using 2 models. We're using this, at the surface, something called the soil water balance, or SWB model, that calculates how much irrigation is going to go in to the ground. And then we combine that with a groundwater model called ModFlow, which is just the name of the computer code we use. And that's what's going to calculate our groundwater results, stream flows and water levels and so forth. So we link these 2 models together. We do a lot of work in this model looking at land use. This is a map of the different crop types in a particular year in our model area. The different colors represent, say, the brown are potatoes, and the green is corn, and the yellow is sweet corn, and then we have soybeans. So we need to think about the crops because each crop uses a different amount of water and requires a different amount of irrigation. And then on the right, you do see the irrigation. These are the irrigated fields. So these are places where we had to carefully calculate the water balance and account for both the water use and the water that comes back, or the recharge from that irrigation. And when we put all that together, we also have to look at water use. The other interesting thing about this area is, unlike Madison, where water use is fairly steady throughout the year, in this area, water use is very unsteady. So looking at the graph on the left, So this is a graph of pumping in million gallons a day, and that goes from 0 to 160 million gallons a day. At the very bottom, you see non-irrigation water. So there are some Village of Plover wells, for example, run year-round, and they're pumping, something like 10 million gallons a day year-round. The irrigation wells, though, turn on in about June, and they go through usually August, and when they're going full blast, they're up to almost 120 million gallons a day. So there's no pumping from irrigation wells for several months of the year, and then in the middle of the summer, there's a lot of pumping. So we have to think about how to partition that pumping over the year. On the right is, again, our model basin with the wells by the diameter of the circle represents the magnitude of pumping. We can focus again on the Little Plover Basin, which is here, just to demonstrate that there are a lot of wells right near this river. So it's not a big stretch to imagine that the wells are going to have some impact on the river. When we go through our soil water balance model, we calculate annual recharge. We actually calculate monthly recharge too, and I'll show you that in a second. But we do that in a very spatially variable way. So all the colors here represent different amounts of annual recharge. If you look at this bar graph goes from 0 to 18 inches per year of recharge. You can see the median is something around 10 inches a year. And we look at what the different crops are using: corn, sweet corn, grass, and so forth. So 10 to 12 inches a year about what we're getting here. You can see that the irrigated area has different recharge than some of the non-irrigated area here, and you can see the moraines showing up. So geology and soils is very important in figuring out recharge. When we parse that out through the year, it's interesting to see when recharge happens. So each of these is a map of a month, and throughout the year, and the color bar goes from 0 to 6 inches per month. And so you can see that there's hardly any recharge in the winter, in January, February. The ground's frozen, there's snow sitting there, but there's almost zero recharge. Recharge picks up in March, and it really takes off in April, as you might expect. The snow is melted, the crops aren't growing yet, and it's raining a lot. April, May, and June, we're getting recharge. Then we get into the summer, we have a lot of water use by crops. We have some recharge, but not a lot. And then it picks up again in the fall, but falls off in the winter. So it's, again, the recharge is a transient, or something that's changing with time. And that's something we had to calculate for our model. So let's look at our model a little bit. What do we get out of it? Well, here's just a map of some results. As in the Dane County model, we get contours of water levels. Groundwater flows perpendicular to these, and some of it's going to end up in the river. Well, that's all very nice, but what we really want to know is something about the river, water balance in the river and drawdown from these wells. And so we can start to use the model to make these calculations and to look at scenarios of management. So I'll show you a couple of those. For example, I want to know where the water in the river actually comes from. Well, we can do that. I showed you earlier some capture zones or contributing areas for wells. Here's a contributing area for the Little Plover River. So this is the Little Plover River here. This is its surface water basin, and the blue shading is the groundwater contributing area, again looking into the past before there were any wells. So we turned off all the wells, no wells in this simulation. And so you can see this area is where the water would have come from 70 years ago, before there were a lot of wells. All the groundwater in this area ends up in the river somewhere. Some of it ends up upper in the headwaters, some of it enters the river down here somewhere. But we can look at this map and we can understand that the natural groundwater basin, interestingly enough, is not the same as the surface water basin. In fact, it's a little bit bigger. And again, this is largely because the landscape up here in the Central Sands is so flat, so the groundwater basin and the surface water basin can be different. More importantly, the size of the capture zone is proportional to the base flow in the river. In other words, we have to account for catching enough water to supply the base flow. So the size of that blue area is proportional to the amount of flow we would measure if we measured the stream. Now let's move forward to the present day and add wells. So all the dots are pumping wells. And again, I've done another capture zone, but the capture zone looks different now. It looks smaller and it's kind of got a funny tail on it. And that's because these wells are taking water that would have gone to the stream, but it's not going to the stream anymore, it's going to these wells. And so the wells are sort of interrupting the flow that was going to the stream, and they've made the whole capture zone smaller. This is called diversion. Water has been diverted from the stream, and not necessarily pulled out of the stream, but water that would have gone to the stream didn't get there. And as a result, this area is smaller, and the interpretation of that is now there's going to have to be less stream flow because we're capturing less water. So there has to be less stream flow because we have to maintain our mass balance. So the area of capture is now smaller in size because pumping has diverted water that would have otherwise gone to the river. It's interesting that even wells outside the basin are contributing to this diversion. So even a well that's not really in the surface water basin is having an impact. And the flow in the river is going to proportionally decrease. So we can understand why there's less flow now. And we know there's less flow because people have measured it over the years. And so this is a hydrograph of real data from this represents from 2005 up to 2014, flow in the river at one point. And the red line represents the historic low flow back from 1959 to 1987. And in other words, that was the lowest they ever went, and you can see that in recent years it's gone lower than that. The dashed purple line represents the minimum public rights flow that's been set by the DNR as representing the flow that's necessary for aquatic life, for fish reproduction and so forth. And you can see the river has been, in recent years, frequently, not always, but frequently lower than that. And in fact, we have evidence that it dried up completely in 2009, something that apparently never happened in the past. So something's changed, and we know with our model what has changed. We have all these wells. So now the question is, how could we remedy this? And so here's where we can really use a model to look at scenarios, management scenarios, and test them with the model before we have to test them in the field. And we've had many discussions about what to do, such as taking away drainage ditches, move industrial infiltration, of which there is some, to a different place in the basin, converting pine plantations to prairies, taking selected wells out of the, or fields out of production, changing crop patterns, showing how much water is really permitted. It's interesting that there's far more water permitted than is actually used. Changing the municipal wells, many things and many others that we could think of. Let me just show you how we would look at one of these scenarios. So this was a scenario actually suggested by the potato and vegetable growers. They said, well, because they're interested in solving this problem, here's the river, and they said, we got some land here, suppose we shut off 11 wells that are in this shaded area here. What would that do? Would that have a big impact or not? Because some people have said, oh, if you just shut off all these wells, that would solve the problem. Others have said, no, it wouldn't. Well, let's find out. So we go to this area, and within that circle, find 11 wells that they thought could be shut off. And then we're going to see what that would do to the flow at these gauging sites along the river. There were 3 or 4 places where the river flow has been measured. And when we do that, we get this. So this is a map of what you might call draw up or increased water levels. If we turn off these 11 wells, we would see the water table would rise a foot or more in these fields, and then up to half a foot, even a mile or so away. So that's a pretty significant rise. And flow in the river would indeed increase. It would pick up at this Kennedy gauge, this is Kennedy Avenue, by about half a CFS, Eisenhower Avenue about half a CFS, and at Hoover Avenue about 0.6 cubic feet per second, or CFS. Now that's not enough to solve the whole problem, but it shows you that that's a pretty significant change that could be made here. It's a trade-off, though. So this particular scenario, which again is just a scenario, it shows us that we could gain between 0.5 and 0.6 cubic feet per second back in the river, and we could raise the water level near these wells by shutting off these wells. But the trade-off is that some fields would have to either go out of production or get their water from somewhere else. You know, maybe they could pump it out of the Wisconsin River, or they could pump it from industrial wastewater or something like that. So now we have, you know, we haven't solved a problem, but we've given decision makers a choice, some information that they can use for making a choice, and we can do many, many other scenarios like this. So I hope I've convinced you that models are really, the way we use them are decision support tools for understanding the impacts of new wells, for understanding alternatives, for looking at these groundwater, surface water relationships, understanding where water comes from a spring or a lake, to a spring or a lake, and how changing the environment might change that flow. And we can also look at things like climate change. How is groundwater going to respond to that? Land use change, if we take some fields out of production or we pave them over, how is that going to affect things? Wellhead protection. I didn't talk about cross-connected wells, but if we drill wells through aquifers and it connects the two aquifers, that can have an interesting impact on the system. And then we can also use them to look at well and water quality problems. Many, many things that I don't have time to talk about this morning. I've talked about two models. We have models that we worked on for many parts of Wisconsin. Here are just a few examples of that, including we've worked on some in Door County, as some of you know. And so this is one of the things we do with our partners at the USGS. And then just finishing up, I want to acknowledge some of my colleagues who I work on these things with, and there are certainly others I haven't thought about. Thank you for your attention.